Hello students, welcome to lecture 1 of the online course on Introduction to Microwave and Optical Metamaterials. So here is the lecture outline. We will discuss about a brief overview of the electromagnetic spectrum. Then we discuss what is the need of metamaterial in this current era. What are the building blocks of these metamaterials, which are also known as meta-atoms. We'll go into the history of metamaterials and discuss about the timelines and classification of metamaterials. And in this particular video, we'll discuss about the development and application of microwave metamaterials. So before we begin the course, let us have a quick look at the entire electromagnetic spectrum. So as you can see, the EM radiation or electromagnetic radiation occurs over an extremely wide range of wavelengths, starting from radio waves, which are measured in several hundreds of meters, down to gamma rays, which are basically 10 to the minus 12 meters. So here you can, just to visualize the wavelength, here is the approximate scale of the wavelength. So radio waves are like of the order of the building, okay. Microwaves are in this particular range, okay. This is how the visible wavelengths are, and when you go down to gamma rays, they are basically of the size of the atomic nuclei. So here is the corresponding frequency spectrum for these wavelengths, okay. That's also really wide, you can see 10 to the 4 hertz to 10 to the 20 hertz, okay. And this particular scale shows you the temperature of the objects at which this particular radiation is the most intense wavelength that is emitted, okay. What does it mean? So if you take an object which is 100 Kelvin, okay, or minus 137 degrees centigrade, that will do this black body radiation with the dominant wavelength in this particular range, okay. So what is important here? To quickly remember the frequency and the wavelength conversion. So for that you can use this frequency wavelength cheat sheet, okay. So it tells you the speed of light in vacuum is given by c, that is 3 into 10 to the power 8 meter per second, or you can also write it as 30 gigahertz centimeter. That means if you have 30 gigahertz frequency, you will have 1 centimeter as wavelength. If you have 3 gigahertz frequency, you will have 10 centimeter wavelength, okay. So you can use this cheat sheet to convert wavelength and frequency, okay. Now in this particular course, we will be focusing mainly on microwave and visible radiation. So microwave, as you can see, the frequency range is from 300 megahertz to 300 gigahertz. That means the wavelength will be from 1 millimeter to 1 meter, okay. And in the visible, we are going from 430 terahertz to 780 terahertz, okay, and the wavelength range is from 380 nanometer to 700 nanometer. So these are just to tell you that we are basically focusing on microwave and visible in this particular course. There is a particular reason for focusing on these two, okay. So all the experimental initial demonstration for metamaterials were done in this particular domain, microwave domain, because it's easy to fabricate those metamaterials, as we'll discuss and see in this particular course, okay, to prove any concept that is also going to work in any other range, typically in the visible range as well, okay. Now the question comes, what is the need for metamaterials, okay, or you can say why metamaterials? So many materials are already there. So modern material engineering basically leads to the synthesis of many novel chemical compounds, okay. So a lot of work has been done in chemistry, chemical engineering, by combining atoms of natural materials to obtain some desired electromagnetic property. So this is the kind of chemical matter we have learned till now. So there are pure substances which can be elements or compounds. Elements are basically having only one kind of atom. compounds will have 2 or more different kinds of atoms, and then you are also having mixtures, something like alloys, where solid mixtures of metals take place, solutions where the liquid mixtures of compounds take place, or you can also have blends and composites, which are basically solid mixtures of compounds. Okay? So, with all these things in place, okay, still there is a requirement that for a particular frequency range, they are not able to provide or give you a custom required electromagnetic property like permittivity or permeability. We will come into the definition if you are not sure about this, okay, in the upcoming slides. But then they basically tell you how electric and magnetic field behave with a particular material, right. So, engineering devices made up of novel compounds, okay, can exhibit combined or modified electromagnetic responses of its constituent materials. Okay. However, there is a limitation or bottleneck in this particular thing, is that there is a limited set of natural materials which appear in the periodic table. So, it basically exhibits a fixed set of electromagnetic property, and you cannot tune everything, though you can mix things up and can go closer to a different kind of property, but you cannot create something completely new or unusual, right. So, for that matter, for your convenience, I am just showing you the periodic table, which has got 118 elements, okay. And prior to the development of metamaterials, researchers were stuck with these basic elements only, and their mixtures and combinations to realize any new properties. But when you go for metamaterials, that is where you could design materials with properties which are completely independent of their chemical composition, and that opens a whole new area where that opens up a whole new area where you can engineer the design and change the electromagnetic behavior of that particular material. Okay. So, what is basically defining those? Okay. So, you are basically looking for a material's electromagnetic behavior should be decided not by its constituent atoms or molecules, but by the physical arrangement. Okay. And that is where metamaterials are way better, in the sense, in terms of flexibility they provide as compared to the natural materials. So, natural materials are composed of atoms. Similarly, metamaterials, which are artificial materials, they are basically composed of unit cells, which can be called as meta atoms. Okay. So, what is meta? Meta means beyond, it is a Greek word, okay, beyond or after. Materia means it's material, right. So, you are basically telling that where the natural materials stop, you can start using metamaterials to obtain those exotic or extraordinary electromagnetic properties. So, what we learned from here, that metamaterials are basically composed of meta atoms. They are artificial atoms or engineered unit cells. Okay. So, and this particular term metamaterial was introduced by Walsha in 1999. Okay. So, nature uses atoms to build materials. Okay. So, and the interaction of these materials with the electromagnetic wave is governed by the frequency dependent material properties, such as dielectric permittivity and magnetic permeability. The interaction of these materials with the electromagnetic waves is governed by the frequency dependent material properties, such as permittivity epsilon f and permeability mu f. So, all the naturally occurring materials have positive permeability and positive or negative permittivity, like metals have negative permittivity, right. And these are the properties that govern the electromagnetic responses of these materials. However, for various modern technological advances in communication, imaging, sensing, engineers basically demand precise control over the behavior of the electromagnetic waves when they are interacting with the materials, okay, to achieve some specific functionality. Okay. So, in that matter, okay, or in that particular direction, when you are using metallic, semiconductor or insulating structures to design meta-atoms or the unit cell, okay, for the metamaterials, you can basically obtain that kind of control over the materials property, so that you can guide or make the electromagnetic wave behave in the way you want. So, metamaterials can provide tailored or artificial responses because you can create negative permittivity and permeability, okay, over a specific electromagnetic band. So, at the end of the day, a question can come to your mind that these meta atoms are also made of some material, and how about the properties of those materials dictating the overall property of the metamaterials. Now, this is something interesting because in metamaterials, okay, they show electromagnetic properties not depending on their raw material composition, but from the assembly of the sub-wavelength size individual atoms or individual elements called meta atoms. So, you can see you have these atoms. With that, you are forming a material. That material you are using to form your unit cell design, which is a meta atom, and the periodic arrangement of this meta atom, it decides the overall property of the material that you are making. Okay? So, your metamaterial properties are essentially independent of the constituent materials properties, right? So, meta atoms can resonantly couple to both the electric and magnetic components of the incident electromagnetic waves. So, that is how meta atoms work. They are basically made of conventional materials only, just like metals and dielectrics. And one important feature is that these meta atoms are sub-wavelength size. That means the size of the unit cell or the meta atoms is much smaller than the wavelength of the electromagnetic wave they are interacting with. Okay. So, they are much conventional than optical elements such as lenses and prisms. So, metamaterials cannot be obtained from any continuous and homogeneous medium, and this is why the metamaterials are always a composite nature. Okay. So, usually metamaterials are constructed from discrete, resonant, micro and nanoscale objects depending on the frequency range you are targeting. Like if you are going for optical metamaterials, they will be nanoscale objects. If you are working with microwave metamaterials, your unit cells may be in millimeter scale. Okay. The whole idea is that you got to have the meta atoms sub-wavelength in size. Okay. And this will mimic the electromagnetic reaction of atoms and molecules of natural substances to make them interact with light and other forms of energy in specific controllable ways. So, here is a brief outline, or here is a brief timeline of this metamaterials. So, you can see on the left that it all started with Soviet physicist Victor Vassilego, who theoretically proposed left-handed materials, LHMs, okay, with simultaneous negative permittivity and permeability, predicting unique wave features such as negative refraction. Okay. However, because of the absence of natural left-hand materials, no experiment could be conducted at the time to verify this kind of predictions. And then there was a long wait until 1996, where Sir John Penry from Imperial College London, he proposed a wire structure to realize negative permittivity. So, there you can control the dimension and the periodicity of the wires to control the plasma frequency. So, you can make artificial metal. Okay. So, that way you can achieve negative permittivity over a particular wavelength range. In 1999, Professor Pendry again proposed split ring resonators that could realize negative permittivity. Okay? So, with that, when you have both negative permittivity and negative permeability artificially created or designed, in 2000 and 2001, David Smith was the first to realize a medium with an effective negative index of refraction. Okay? So, that is when the perfect lens was proposed by Professor Pendry and David Smith. They made this device which is shown here, okay, the first negative index material or metamaterial. Okay. So, in this flow chart you can see from 2004, 2005 and 2006, a lot of revolution happened in this area of metamaterials, where people have looked for gradient refractive index medium, transformation optics, optical cloaking, okay, and then new areas came up or application areas emerged like super lens, acoustic metamaterials, generalized Snell's law, creating hologram, Huygens metamaterials, and then right now in 2014-17 people have worked towards dynamic metamaterials, the intelligent digital programmable space-time variable metamaterials over this years 17, 18, 19, and recently people are also focusing on auxetic metamaterials in smart materials and structural systems. So, these are kind of mechanical metamaterials. People have involved AI in designing the unit cells to give you unique properties. People are designing metamaterials for 6G communication, for bioimaging and whatnot. So, a lot of things happening in this area of metamaterials and meta surfaces, which are basically the 2D version of these metamaterials. Now, the important part in metamaterials is also to classify the materials. Okay. So, this classification is done by these two important properties of material, which is the permittivity epsilon and permeability mu. Okay. So, these are the properties of every material. So, this basically measures the opposition offered against formation of electric field for the case of epsilon. Okay. So, it tells the number of charges required to generate 1 unit of electric flux in a given medium. Similarly, if you think of permeability mu, that is basically the measure of the ability of the material to allow formation of magnetic lines of force, or you can say magnetic field within. So, it basically speaks of the ability of magnetization that material possesses for any applied magnetic field. So, on the basis of permittivity and permeability, okay, that is epsilon and mu, the materials can be classified into 4 groups. So, you can see the top right first quadrant, this one. So, here the materials have both permittivity and permeability as positive. So, it is also called double positive materials, and most occurring media like common transparent dielectrics, they fall in this category. So, you can see that if this is E and H, okay, they follow the right hand rule. So, you can find the wave propagation vector and the Poynting vector, both are in the same direction, perfectly fine. So, this is where the common dielectrics are lying. Then you go to the second quadrant or the top left quadrant. So, here the material has got negative permittivity, but positive permeability. So, it is also called epsilon negative material in certain frequency range. So, here waves cannot propagate, as you can see there is evanescent waves, okay, and there are metals which behave like this in optical frequency range. Okay. The bottom right, this one is the fourth quadrant. So, here a material has got positive permittivity, but a negative permeability. Okay. So, it is also called negative mu metamaterial, okay, or material. So, in certain frequency regimes, some Gyromagnetic materials can exhibit these characteristics, but typically not naturally occurring at optical wavelength. So, here also waves cannot propagate, it can only support evanescent waves. Okay. Now, the most important quadrant in this metamaterial field is this third quadrant, where, or this bottom left quadrant, where a material gets simultaneously negative permittivity and negative permeability. Okay. So, it is also called double negative material, and this kind of metamaterials or materials can only be fabricated artificially. Here you can see the E and H will have the wave vector in the other direction, that is, it is following the left hand rule, okay, whereas the Ponting vector goes in the right direction. Okay. So, here also we can quickly see the engineered materials which can give you this kind of properties. So, this tells you the natural materials happening over here. Then in the second quadrant, here you can see an array of metallic rods can behave like metal, giving negative permittivity over a particular frequency band. You can have an array of split ring resonators which can give you negative permeability over a specific band, and when you club them together and make an array of rods along with array of split ring resonators clubbed together, you can get simultaneous negative permittivity and permeability. So, with almost limitless possibilities of designing these meta atoms, you can understand that metamaterials offer unparalleled design flexibility. Metamaterials with its electromagnetic properties are basically dictated by the physical structure that can be designed for applications across microwave and optical frequencies. So, here is a complementary split ring resonator structure. These are basically copper patterns on FR4 substrate based microwave metamaterials resonating at 13.5 gigahertz. So, the wavelength is around 22.22 centimeter. So, here you can see the period and the size of the element. So, they are all sub wavelength. Okay. Similarly, on the optical regime, here you can see the scale is much smaller. So, this you can fabricate easily, this you have to go for nano fabrication. So, this scale is around 50 micron. So, here also it is a complementary split ring resonator structure. These are again copper patterns in quartz substrate. So, these are working on optical regime or optical frequency band. So, F is around 1 terahertz. Okay. So, lambda is typically 300 micron. You can see the periodicity and the element size. So, they are sub wavelength. Okay. So, here what I want to show that the same concept can be applied in microwave as well as optical regime. Okay. So, this is how metamaterials can be designed for specific applications. So, a quick overview of the development of microwave metamaterials. So, here the concept of left hand materials were received almost 30 years before the realization of the first negative permittivity using artificially composed metallic wire arrays by Sir John Pendry, and that was done in the microwave frequency regime. So, as you can see, there is a structure that represents an array of thin metallic wires. So, P is basically the periodicity, and when you have electric field applied along the axis of the wires, they generate a current in them which produces equivalent electric dipole moments. So, when you average them, the dipole moments reveal the structure's permittivity with a plasmon type frequency dependence, and you can see the relative permittivity of this structure takes this particular form, okay, where omega p is basically the electroplasma frequency, and that depends on the physical parameters, that is P and A. What is P? But that is basically the wire spacing, A is the radius of the wire. So what you can see here, the metallic property, what metal you are using, that does not appear here, and that is how the structure basically defines the property. What is C? C is the speed of light. Okay, so sigma plays a bit of role in the damping, because that is where the material parameter will get in. Okay, so how wide or the resonance will be, or the damping parameter will take care of the conductivity. So this is where slightly the material of this wires will get into, but typically you can see you can design a new material with a custom made plasma frequency. Okay. So what you have to remember here, that the interparticle spacing is much smaller than the wavelength of the light or wave that is propagating through this structure. And when people have achieved getting artificial structure giving you negative permittivity, next people have done to explore what structure can give you negative permeability, and that is also done by Professor John Penry. He demonstrated that complementary split ring resonator structure can give you negative permeability in gigahertz range. Okay, so this is the design of the complementary split ring. So this is a C, and then you have opposite kind of C over there. These are the structural parameters, all in millimeter range typically. So if you want to make a 3D symmetric design, so you have to stack this kind of structure on each side of the unit cell. So finally you can use this one and repeat it periodically. Okay, so this is how the stacking has to be done. So one split ring resonator is here, the other one will be below. Similarly on all three direction it has to go, okay, replicate itself. So that is how you can make a 3D cubic symmetry structure. So here I just copy pasted the unit cell to show you. On the top surface you have, so there is nothing on the bottom surface. This top surface will go and like align with that. Here also on the right surface you have, so the left surface is blank, so the right surface will be periodically extended. Okay, top surface is periodically extended, and then the whole thing, the plane, you can think of extending in the y direction. So that is how you can make a structure with cubic symmetry. And once you calculate the resonant frequency of this kind of structure, you can see that they all depend on the structural parameters like R, C, D, okay, L. So all these parameters are shown here. L is basically this particular spacing. So here also you understand that the frequency where the negative permeability will be seen basically depends on the structure. So that is how you are able to make materials, artificial materials, for giving you custom made permittivity and permeability for a particular frequency range. So with that, when you have two things ready independently, you can mix them together. So effective negative permittivity and negative permeability from the split ring resonator, the first one was coming from the metallic rod metamaterials, were combined together. So why not you make a unit cell like this and repeat it periodically. So this is the structure, okay, that can give you both permittivity and permeability negative simultaneously over a particular frequency range, and that is what was called the first demonstration of negative index material or left hand metamaterials. Okay. So the design was shown in microwave region, but its dimensions can be scaled down for operation at the optical frequency. So this is the first photograph of the left hand material sample. So you can see that there are split ring resonators made on fiberglass circuit board material. On the back side there are these metallic wires, okay, and then they have been assembled into interlocking lattice to make this kind of a structure, and this was the actual calculation of negative refractive index. Okay, it shows that you are actually able to get negative refractive index for this left hand material over 10 gigahertz. Okay, so there are some asymptotes because of the limitation of the measurement equipments. Teflon was used as a reference, but you can see at this particular frequency you are able to get negative permeability, negative index of refraction, right? So this structure was built at the University of California, San Diego by Smith and Schultz. So they actually brought the two things together, and this was the first demonstration. And this has opened a lot of applications, a lot of interest among the researchers, that you can now design your own material. You don't need to depend on natural materials and be limited by their particular wavelength range or dispersion diagram. You can create material with desired refractive index, with desired permittivity or permeability. So you can actually control the way electromagnetic wave will interact with your designed materials. So with that, we'll stop here, and if you have got any queries regarding this particular lecture, you can always drop an email to this particular email address, deb.sikdar@iitg.ac.in, but make sure you mention MOOC and the course title on the subject. Thank you.